For those of you that are in the back, you might want to come up front. We've got about 50 to 60 lines of code, 8-point font. It goes by really fast. We're sniffing you too. All right, so let me go ahead introduce Nick Miles and Chris Lynn. How many of you were here in the last two sessions? All right, yeah, we got some pen testing, red teams, threat hunting, physical and IT security breaches, war walking, Wi-Fi sniffing. This gets even better, IoT sniffing. Any IoT sniffers? Well, Nick joined Tenable as a research manager in 2011. He has written hundreds of Nessus plugins and developed several core libraries used in the Nessus engine. He now leads the company's zero-day research team. In his free time, Nick likes model aircraft, metalworking, and breaking out his telescope on clear nights. And then we've got Chris Lynn here. He's a senior researcher on the zero-day research team as well with Tenable. He's passionate about security. He enjoys attacking targets ranging from web apps to IoT targets, people in the audience. Outside of work, Chris enjoys playing competitive tennis and the occasional craft beer, which, of course, Tampa's a great place for craft beers. It's all yours.
Hello. Hi, and welcome to our talk, and this is about extracting an ELF from an ESP32. As he mentioned, I'm Nick Miles. I'm zero-day research manager for the zero-day research team at Tenable, and this is Chris Lynn, who is a senior researcher on the zero-day research team. So we're going to talk about ESP32, what it is and what it's used for. So here is an ESP32 development kit. And the chip we can see that we're interested in is highlighted in the green box. And as you can see, it's pretty small. So it's a complete system on a chip. And there's a flash chip that is on there too. It's below. It's right there. And it's up to 16 megabytes in size is what it supports. And that's the board we actually use for testing and finding a vulnerability in SimpliSafe, which we're going to talk about. So it supports Wi-Fi, Bluetooth. It has 2 cores, and it's really popular in IoT devices. So cameras, light bulbs, appliances, wearables, alarm systems, which we'll talk about. And it's either used as a standalone system or as more commonly as a slave for talking through Wi-Fi and Bluetooth. So it reduces the overhead on the core application, microcontroller, or processor. So this is how it's designed. There's 2 Extensa CPUs, and they're labeled App CPU and Pro CPU, which you would think that would make you think that they are both dedicated to doing certain tasks, but they're not. They used to be. They moved away from that to an asymmetric design where both the CPUs can be used interchangeably. And they both use the same addresses to access memory, with a few exceptions, being that the RTC fast memory can only be accessed by the Pro CPU. And it can support 13 peripherals that are equipped with DMA, and and also obviously there's flash memory on it too. You can program. So this is the device we found one of these on. This is a SimpliSafe 3 or SS3 alarm system. And this is it's the base station. So you have sensors, you have a keypad, and you have the base station that organizes everything. It talks to the cloud. It talks to all the sensors. It has a Wi-Fi chip in it, which is on the ESP32. That's how it talks to the internet. It has a cell radio. It has another radio for talking to all the sensors, which we'll talk about. And there it is inside. You can see it here. So on one side of the board, there's the ESP32, and that's used for Wi-Fi and Bluetooth. And on the other side, there's a TI CC1121 chip, I believe, and that's used to talk to all the sensors on a 433 megahertz network using frequency shift keying. And we actually decoded that protocol, but it wasn't very helpful. So, problem we ran into. So the first thing we wanted to do is actually look at the firmware on this chip and figure out what's there. So to get the firmware off, we found the easiest way was to desolder it from the SimpliSafe, get a development board, and replace the flash chip on the development board with the flash chip on the SimpliSafe. It's really easy to do that with a heat gun. If you don't have a heat gun, there's something called Chip Quick, Q-U-I-K, and it's like solder that stays molten for very long, like several seconds. So you can basically just splash it across the pads and pull the chip off really quickly. It's really easy, really nice to use if you just have a soldering iron and want to do this at home. And then you can use the dev kit that comes with ESP32 to access the flash and dump all the contents, which we did. And we ran it through file, and obviously it is data. So we used our next favorite tool called binwalk, and we ran it through binwalk. And it really doesn't tell us a whole lot. There's a bunch of paths. There is some SHA-256 constants, some certificates, some private keys. But we needed to figure out how all this data is organized so we can do a static analysis. We don't see any binaries or anything obvious to look at. So it would be nice if we could come up with a way to process this flash, put it into a format we could parse, and have it be repeatable. So we need some sort of, a little script or a tool to do it, which is what this talk is about. So we looked to see if there was anything that would do this for us. There are a couple of different things. There was a good blog post on Board Pen Tester about the previous version of this chip, the ESP3266, but we couldn't use that research on our new chip because it wasn't backwards compatible. We found an IDA plugin for reading the machine code from Extensa CPUs. So we did end up using that. That was pretty helpful. There was a plugin for IDA for loading the ESP8266 parts of the firmware into IDA, but it didn't work very well, and it was designed for the older chip. And there was also another new IDA loader by Joe Rosner, which I haven't looked at, but apparently it's supposed to do some of this. But we just found out about that recently. So this section will be dedicated to discussing the firmware and the image layout, and it will serve as an intro to the section that follows. And this will largely be a discussion of the online documentation, but we'll teach the audience the foundational knowledge that you need to understand the build process. And we'll look at topics such as partition types, image sections, and over-the-air updates. So, the goal, like I said, is to take a flash dump and extract an ELF. And then if we get an ELF, then we can load that into IDA. No problem, because IDA can understand ELFs, and it can parse out all the sections and understand it. So in order to extract an ELF, we need to know the composition of the flash contents, and we also need to understand the build process. So the first thing we need to understand is there's two bootloaders that the ESP32 uses. One is stored in ROM, and it's a first stage bootloader, and the second stage is stored in flash. And the first stage doesn't do anything other than just load the second stage in the RAM and then hand off execution. And then the second stage starts. And if I talk about bootloaders anymore in this talk, I'm talking about stage 2. And this bootloader is stored in flash address, a fixed address at hex 1000. So this is actually what loads and boots up the application image. So first, the bootloader reads the partition table, which is at hex 8000. That's a default location, and that will tell you where all the apps and the data and everything is found. And then it will pick a partition to boot up to. There could be multiple app partitions because you can over-the-air update this chip. So there's a factory partition usually, and then another partition gets placed when you update it with data. So it chooses to see which partition it should boot to, checks to make sure they're healthy, and picks one and boots. And here's an example. This is actually the UART log for the SimpliSafe that we reversed engineered. And you can see there's the first stage running. So it's doing the hardware configuration. This is all hardware configuration. And then it goes and starts loading the second stage bootloader into memory. And then the second stage bootloader, you can see it right here, loads. You can see that it reads the partition table. That's a pretty typical configuration. We'll talk about that here in a second. But there's the data partition where that basically has the information to determine which partition to boot to, which app partition. And these two are the app partitions. So then it picks to boot this OTA1 partition. You can see the offset matches this offset. And then it switches to stage 2. So, like I said, this partition keeps track of which partition to boot to. It's part of the over-the-air update process it's written to. This here keeps track of some physical configuration information, but it's not really used that much anymore. You can actually get rid of it if you need to save space. It's built into the apps now. This here we'll talk about, this is called non-volatile storage. It's like a little miniature key value pair file system that you can use. There's a API in the dev kit to use it. This here is a BLE data partition, and it has a little binary that if you're using the chip, if you're using the device as a BLE Bluetooth server, you'll put this on there. And there are the two data partitions, and there's usually like a factory partition also. And there's usually two other OTA partitions, but this one just uses OTA 0 as the factory partition, and a lot of them will do that to save space. So the reason it's booting from OTA 1 is because OTA 0 is the factory built-in partition. So somewhere along the line, it got updated. Data 1 on OTA 1, it updated the OTA data, and then the device is booting from the updated partition. All right, so now that we know how the flash is laid out and what the partitions are, we'll be examining how the data is structured in the application partition. And these are the OTA data partition and the factory partition, and it's available. So all these partition types that you might see. All right.
Can everyone hear me okay? All right, so now we'll be talking about the application format. And like Nick said, the bootloader has to pick an app. So we had to understand what that app looked like. So an app partition, it has a very specific structure. As you can see, it starts off with an app header. And then, we have either code segments or data segments. And so each segment will have its own header, and then data. You can have any number of segments. And then also we'll have a checksum byte and optionally a SHA-256 and a digital signature for integrity verification. And so if we drill down a little bit deeper into the app image header, you can see that it's broken down into a common and extended header. So if we run through these fields here, you'll see we have a magic word. So that just lets the chip figure out that this is an app image header that's starting. Then we also have a segment count, and then there's some settings there that tell the chip this is how fast to read the chip here, and also how big it is. Like our flash chip was 4 megabytes, so that would be in here. And also we have entry point address. So where does the code start? And if in the extended header, we have some settings here like write protect pin, spy pin drive settings, and also the chip ID. And then this piece is important here. It tells the chip whether it can actually read this image or not. Then we have a reserve section here, and then another SHA-256. So the segment header is a little bit simpler here. We just got 2 fields. It specifies where the load address will be, and then also the length of the data. And so, like I said, we have 2 different segment types. You can either have code or you can have data. And so if you, like an app segment type is going to have code, and you can store it in 3 different segments in memory. You have IRAM, IROM, or RTC fast memory. And so IRAM that's instruction RAM. And it does have a specific purpose. So a few of the components, like of the development framework and then the Wi-Fi stack are placed in here. And also the developer, like let's say they want the code to run faster, they'll say, they'll specify that the code should be run from RAM. And then also we have iROM. That's code executed from flash. And the difference here is that the memory mapping unit will have to be used to actually put it into RAM. And then also the device has the ability to go into low power mode. So if that were the case and it needed to wake up from like deep sleep, it would use RTC fast memory. And so on the data side, we, similar concept here. We have 3 different regions, DRAM, ROM, and then RTC. So generally, the non-constant data and zero initialized data goes in that DRAM section. And in DROM, again, that's flash. By default, we have constant data stored here. And then as we'll see in the next slide, there's a specific purpose for that DROM segment, and that's describing the application. And then also, like I was just talking about with coming out from deep sleep, we have RTC slow memory. So that'll store globals and statics related to that kind of code. So the DROM segment I just talked about, which is the application description, it has its own format. At the top, it has its own magic word. We have a secure version, and that's for anti-rollback purposes. We also have 2 reserved fields that aren't used at the moment. But then most importantly here, this segment, it tells you the application version, the project name, compile date and time, and then also the version of the development framework that was used to create the app. And also we have a SHA-256 of the ELF file. Okay, so now we've kind of got an idea of what that application image format is. We've got an app header, and then for each segment, we've got its own header segment data, and then some integrity verification stuff. So if we zoom out a little bit, in our grand scheme of things, we want to take it ultimately to IDA Pro, right? So that's kind of where everything fits into the flash. So now we can kind of start taking a look at the build process of how the firmware is built before it's put onto the device. All right, so bear with me. I know the code's kind of small, but in order for us to understand the process, we started off with a Hello World application. So we've got some C code, kind of like you would use with an Arduino or whatever. But basically, it's going to print out Hello World. Then it'll print out some chip information, and then after 10 seconds, it'll reboot. So pretty basic. And so when you actually want to build the project and compile it, the development framework makes it really simple. All you do is run a Python script, idf.py, and then pass it a build parameter. And if you were to look into that build directory that has the contents of the output, you would see that you've got number 1, Hello World ELF file. And in case you're not familiar, ELF that's the executable format used on Linux. You'll also have a Hello World bin file, and then a bootloader directory, and a partition table directory. And if you were to look into the bootloader directory, you'd also have an ELF there, and you'd have that binary format as well. And in the partition table directory, you'll just have the binary format. So after compilation happens and you built everything, the IDF will tell you that, okay, now your stuff's built, you need to put it on the chip, you need to flash it. And there's a command that you can run using ESP32, which comes with the development framework. So it tells you exactly how to flash it. And it literally tells you the command. This is the command it told me. And as you can see, the bootloader bin, and then partition table bin, and hello world bin, those all need to get flashed. But we had to figure out where do these binary where do the binary files come from? And the answer is that there's another tool within ESP tool. It's called ELF to image. So it literally converts the ELF to the binary format. And the partition table, a little different. There's no ELF. Instead, you specify a partition table format, kind of like Nick talked about before. and it's in a comma separated value format. And then you can run a tool and it'll build that binary. So if we go back to the command that we were told to use to flash everything, it kind of makes sense, right, with what Nick told us. The stage 2 bootloader is at hex 1000 in yellow. Then we have the partition table at hex 8000, that's in pink. And then our factory app, which is the hello world, got flashed to hex 10,000. Okay, and here's the output we get, kind of same story. And when we run it, we get the expected output. We got hello world, got the chip info, and then it's going to reboot in 10 seconds. Okay, so now we've taken a look at the build process where bootloader starts as an ELF, gets converted to a bin. Same story with the hello world, and that's our app that we want to run. But the partition table goes from CSV to the binary format. Then all of that gets flashed onto the chip. Okay, so now we got to go a little bit deeper here. Now that we know the ELF gets turned into a binary, how does it actually, what's the magic there that happens? All right, so more small code. Apologize for that. But, okay, so we're converting an ELF to the image here. So the first thing that happens is we load up an ELF file, that hello world ELF. And that's pretty basic. There's a custom ELF file class that gets used. So there's a call to read ELF file. And if we dive into there, basically that read ELF file function has the main purpose of validating that ELF file. So it looks at the ELF header structure, make sure it looks good. Also, the CPU architecture of the chip is Extensa. So you might have heard of like x86 or ARM. It's neither of those. It's Extensa. So we're checking to make sure the header entries are the proper size, and then it has to have section headers in order for us to convert it. Okay, and so if that all passes, then we're able to start reading sections. Let me zoom in here for you. And so it chooses sections from the ELF file to include in the application image based on whether the section is of type program bits, and also it checks to make sure that the load address is not going to be 0, and then also the size of the section has to be greater than 0. And so something to take note of is that since we're choosing sections of type program bits, we're actually leaving out the symbol table, and that's really important to reverse engineering, because we need to know function names and variable names, stuff like that. Okay, so just recap real quick. When we load up that ELF file, we first have to validate it. We make sure the ELF looks good, that it's built for the chip. Then we also select particular ELF sections, with program bits, address, and size. Got to check those. So the next part, now that we've parsed out the ELF file, we got to build out the new ESP32 firmware image. So that's the constructor call right here. So since we're not loading a file, this whole section down here does not get executed. And just that top block does. You might recognize some of the fields in here. We talked about them earlier, like the flash read mode, flash size, frequency. Okay, and if we go a little bit further down here, the next thing that happens is we're copying over ELF sections into the new image segments. So first we copy over the entry point, then we copy over ELF sections. And we're able to do that because the image segment is actually a superclass of the ELF section. So if you take a look here, we've got, that's load address, the data in an image segment, and file offset. And the ELF section class has the exact same attributes, so we can just copy those over. Okay, so here's another high level. Copy over the entry point, and then we're copying over ELF sections. And the most important part here, we got to actually save that image. So this method is longer, so I've split it up into a few sections here. But basically what happens is we first create the common and the extended header, like we talked about earlier. And then flash segments and RAM segments are split out based on their address. And so there's a constraint here that has to be checked. Flash segments cannot be in the same 64 kilobyte mapping region. So if that were to happen, as the comment suggesting here, that would be, be indicative of a broken linker script. So when we're writing flash segments, we might have to write padding. And the way we do that is with excess RAM segments, or if we don't have any of those, then we would pad it with null bytes in order to fill up that 64 kilobytes. So here's a graphic for that. We got the 64 kilobytes. Might have to put a RAM segment in there or just fill it up with nulls. The next thing here is just to write out any remaining RAM segments. So if we didn't use them for padding, then we're just going to write them out. And also, if secure padding was needed, we'll end up padding the image so that it ends after signing on a 64 kilobyte boundary. And so after we've done all that, we kind of have to go back in and update the image, make sure the segment count is updated, to include any padding segments. Also, we'll append a digest if needed. And then we'll go ahead and write it out. Okay, so another high-level overview here. So first we create that app image header. Next we have to write out the segments, whether it be flash or RAM. We might end up using some padding, depending on how big those segments are. And then also after we do all this padding stuff, then we'll update the checksum, update segment count, and then update the SHA-256 hash. Okay, so this graphic is I'm trying to help you visualize what we just talked about. So the top here is the conversion that happens when you convert an ELF to an image. And I've added some print statements here. But so if you remember, we'll write out flash segments first. And if we need padding, we'll pull them from RAM segments. So that's why we have these padded segments right here. And then we'll write another flash segment. And then since this IRAM text was used as padding, only part of it was used as padding. So we have to write out the rest at the end here. And this bottom image, it's just showing some information about the image we just converted. So if you look at it, it all kind of matches up, right? So we have a flash read-only in yellow that maps out to DRAM. Then we also have DRAM data in pink that maps out to DRAM. If you were to trace it here, it makes sense. And in the teal, notice that it was also split out as well. And that'll be important moving forward. So here's the observed mapping, just to help you visualize it even better. Okay, so now we've gotten through the ELF to image process. And now we can start talking about our tooling, which is the reverse of that process. And I'll hand it over to Nick.
All right, so our tool can do several things. It can show all the partitions found on the flash dump. It can dump a specified partition to disk. And you can convert an app partition back to an ELF, which I can understand ELFs and load them without any problem. You don't need to build any sort of loader, which is why we wrote this. And it can also dump the contents of the NVS, non-volatile storage partition. So here's what the partition table looks like. It's not a standard partition table that I've seen before. It's kind of strange, but it supports 95 entries, which you'll never use. So there's no way to know how many entries are in advance. You kind of just go through it until you hit an end marker, which has an MD5 sum of all the previous entries combined together. And it's, each field is 32 bytes. There's some magic. A partition type, a subtype, so you can figure out if it's data, or an app. If it's an app, if the partition type is an app, it can be factory or test, and if it's data, the part types can be OTA, RF, Wi-Fi, or NVS. And then the rest of it's pretty self-explanatory. There's an offset where you can find the data. There's a size. There's a label, null terminated string, and there's a flag that's at the end. Right now, all they do is tell you if the partition is encrypted or not. That's all it supports. And that's pretty much it for the partition table parsing. It's pretty simple.
All right, so since we can parse the partition table now, we can pick out an app that we want to convert to an ELF. Whoops, excuse me. So here's our image to ELF, reverse of ELF to image. Fortunately, we were able to reuse some of the code that's already provided with the development framework. So we were able to use this load firmware image function, and it just loads up app segments. So that was super helpful. The next thing that we had to do is create an ELF, and we used this. You can see it down here, but we used the make ELF module to do that. So we're creating an ELF that's little endian with an extensa CPU, and then we copy over the entry point. And again, if we look at that mapping that we used before, we could create a dictionary to map ELF sections to the image segments. So that's why you see DROM is mapped up to flash read-only data. The one thing you might notice is that IRAM 0 is not in there at all, and that's because it's kind of a special case. It's split into two separate ones here, and then also we had to work with that. And also we're not accounting for the real-time clock, so that's on the to-do list. So the next thing that we had to do was define the section header attributes, and we were able to do this based off of the read ELF output. So if you look up here, you'll see, we've got read or write, execute. So these are attributes, and then we've got some alignment stuff here, and we hooked it all up in these dictionaries. So the next thing we could do after creating those mappings and whatnot is we could start constructing the section data. And again, we had to account for the special case where IRAM 0 was split into vectors and text. And then also padding had to be accounted for too. And so then we were able to actually create the ELF sections. Again, they're of type program bits. And then we tack on the section header attributes that we stored in that dictionary. And we added in a string table and a symbol table. The string table really helps with back referencing stuff in IDA. The only problem, we tried to add some ELF symbols in, but we weren't able to use dynamic link library stuff because they pulled out all those symbols. So the next step was to create the program headers, kind of similar to building out the sections. We looked at the read ELF output, figured out the flags here, read write, read execute. As you can see here, IRAM vectors and text were in the same segment. So again, we're building out a dictionary. And so now that we could actually create the program headers, and again, we've got that special case, IRAM 0 vectors. And if we saw that, then we would add on, or that we would append the IRAM 0 text section to create that, that combined program header. And finally, we're able to actually write out that ELF file. So again, this is the reverse process that we talked about before. So our tooling will take a flash dump and convert it back to an ELF that we can then analyze with IDA Pro. And I'll hand it over to Nick to talk about NVS.
NVS is pretty fun. It's a storage system with key value data pairs. It can be encrypted on our Simply Safe device. It was not encrypted, which is a fun thing. Our toolkit can dump it as well. It's basically organized into pages, each containing 4,096 bytes. And the pages each have 126 entries, which contain the key value data pairs. And there's an API for interfacing with this storage system. And it doesn't have any sort of indexing system, and you have to do a linear search to find things, so it's not great if you're storing a lot of data. It says in the documentation not to use this if you're storing a lot of data, use a real file system, but it seems to be really popular to use for development. And basically the way the functions mostly access data is through namespaces and key values. So it looks for namespace and looks for the key, and then it pulls the data out. So here's how a page this is what the page looks like, and you can see a dump of it below. You can see that it dumps the entry state bitmap, and the bitmap basically has 2 bits for each entry, so 252 bits are the 256 bits that are allowed, so it just ignores the last 4 bits. But what's interesting about it is that the erased definition for the bitmap, those fields, those entries still contain data. It's like, when you delete a file in standard file system, it actually doesn't delete the file system, it just changes the metadata. So from a forensics perspective, there's a lot of interesting data that you can pull, including BLE pairing data from previous connections. Here's the storage entry. So it's 24-byte header, 8 bytes of data. For the integer data types, data field actually contains the data, but for the blob and string, the field just contains size information in the CRC32. And the data is contained in the subsequent spanning entries for those. So it doesn't contain any header data, just raw data. And for the blob index, which is like for a big amount of data, there's metadata to enable larger blocks that span multiple pages to be reconstructed, especially if they're not in order. If the namespace field right here in the header is 0, then the entry is a namespace definition, with the key being the namespace name and the value being the namespace index. And you can see an example of that here where there's a definition for the MISC namespace, and the subsequent entry uses that. So it references index 1, which is MISC. And this is a dump of the NVS. You can see here, this is of our Wi-Fi, of our Simply Safe device. And this is actually, we dumped it, and you can see the Wi-Fi credentials in the NVS. So if someone steals your Simply Safe, you probably should change your Wi-Fi password, assuming your router didn't also get stolen. And here's one. This is cool because it's been erased, but you can see the pairing data from a previous Bluetooth connection. So that's really neat. And then demo.
Cool. So now we don't have a video, but we do have some screenshots for you. All right. So like the first thing we do is, we pull the chip out of the Simply Safe, and we have to read it, right? So after we soldered it back onto the development board, we ran the tool that comes with the kit, and it dumps the flash onto disk. And so here's our tool. So we can dump any partition, or dump all the partitions on the flash. So as you can see, we've got the NVS, like Nick just talked about. We've got OTA data, which tells you which app is to be booted. We've got some apps. We've got the SPY FFS. And so if we want to convert one of those partitions, we need to choose an app partition. And so we actually chose one of these, right? We chose app partition app 0. So then it spits out an app 0 ELF file. And so when we want to load it up in IDA, the first thing we had to do was use a third-party processor module for Extensa, because IDA doesn't support Extensa right out of the box. As you can see, we had to choose processor type I can't even pronounce that. Tensilica Extensa. And once we loaded it up, it worked really well, which was surprising. We were able to get this nice graph. I don't know if you can see over here, but none of these function names are named. It's just like sub and then the address. And that's because we didn't have the symbol table to work with. And so the strings looked really good too. I don't know if you can read that, but it says ready for credentials. And I'll show you where that comes from. But if we were to cross-reference it and find where it's being referenced in the code, we ran into this kind of interesting function. And what it ended up doing was it would process JSONs over Bluetooth. So we could connect to the Simply Safe over Bluetooth, and then we could send it a JSON with an SSID, password, and a token, and we could tell the SimpliSafe to connect to a different Wi-Fi network altogether. We ended up reporting this. This was CVE 2019-3998. Not the biggest security issue, but we still found some hidden functionality with our tools, which was kind of fun. And here's a UART dump just showing that process. So we have all of this Bluetooth activity going on, and then it actually read my SSID Chris test, my password, and it connected to my network. So it was pretty fun. And that's our talk. If you want to check out our project, it's on GitHub. You can contribute, report any issues you might find. And then also, Tenable is always hiring researchers, so check out our careers page. And we'll open it up for questions. Yes. It was free. Uh-huh. Yep. Yeah, he asked about the Extensa IDA plugin, and that's free on GitHub. We didn't write it, but someone else did. Yes, sir. Yeah, we'll put them on GitHub. Yep. Anyone else have questions? Yes. I'm going to hand that over to my manager.
So each researcher on our team has a different specialty and different motivations. So I basically let them pretty much choose their targets, although occasionally there are focuses from requests to focus on certain things. So we'll shift focus from time to time. But for the most part, the researchers pick whatever they want, and they usually, do some market research and some showdown searches to make sure that it's, being utilized before they invest a whole lot of time on it, to make sure we get some return on investment out of our research. Because, it's kind of silly to research things that aren't used by anybody. Any other questions? Cool. Thank you, guys.